Greetings, everyone. Since it's already 5, uh, let's begin our seventh live session. The course is being taught by Professor Sanjeev Sabanan, and in this course I have been TAing and I am solving the numerical assignments during these live sessions. So, today, let us begin this session by solving the fifth assignment of our uh, course. So, in this fifth assignment, let's begin by understanding the question number one first. It says that we have to assume an arbitrary metal that forms a Schottky contact with an n-type semiconductor. So it has been given that we have some metal and we have some n-type semiconductor and it makes Schottky contact. It has been given. So now we have been told that we have been told to find the Schottky barrier height. We have been how does that vary if we increase the or decrease the doping. So in here, if it states that how does the barrier height vary if the doping in the semiconductor is decreased. So let us as we already know, as taught by the professor in our class, it showed you how we can form the metal semiconductor junctions. Let me directly go on to the results that for uh, Schottky barrier height in case of n-type semiconductor, let me write it like this: Schottky barrier height and denote it by phi b, that then this will be given by, in terms of energy, q phi b for a metal and some n-type semiconductor, n-type semiconductor junction semiconductor junction. It will simply be given by q phi b, which is the Schottky barrier height. It will simply be given by the subtraction of the metal work function and the electron affinity. So here this uh, q phi m is the metal work function, is the work function metal work function, and this chi s, this chi s of s is the electron affinity, is electron affinity. And in here we are for sure, we know the two things here, that is this phi m, this metal work function, and this the electron affinity. These does not depend on, these does not depend on semiconductor doping, semiconductor doping. So clearly, since our quantity, this barrier, Schottky barrier height, it depends on these quantities, and in turn none of them depend on the doping. So we can clearly say that this remains unchanged with the doping. So the Schottky barrier height remains unchanged with the doping. Now let's move towards another problem. It states that we have been given an metal and it is deposited on a lightly doped n-type semiconductor. So the metal work function is much higher than the semiconductor work function. So we have been told to uh, uh, find how we can make this contact as ohmic one. And we have been told that there are no surface states. So if we have some metal uh, semiconductor dopings, it is likely doped n-type. So in order to, if I consider some case like this, this is the vacuum level. The metal work function is the metal work function, and this metal work function is much greater than the work function of the, and we have been told it is lightly doped. Let me do it like this. This metal work function, and since it is lightly doped, it will be close to the Fermi level. Metal work function is much greater than the semiconductor work function. So let us write it down that this is the semiconductor work function, and metal work function is much greater than this, and this is our, let's suppose this is our Fermi level. So, and this is our valence band H, this is our intrinsic Fermi level, and this is the Fermi level. So we have been told that this if this metal work function is much higher now, then the junction will always be Schottky in nature, because it will try to, the electrons from the n side of the material, from the n type material, will try to move in to the metal side. And since this metal is already a sea of electrons, it has lot of electrons, there will be minimal band bending or no band bending in that side. But in the n side, we will be having the band bending with the at surface, we will be having less concentration of electrons as compared to the bulk. So we will get Schottky contact in that case. So if we now, as rightly said here, if we now use some heavily doped impurity, uh, so we will be having the ohmic contact. So in order to make it, this junction as the ohmic one, we will need this to be as an ohmic contact. So it is simple that we will be needing doping. The semiconductor will be doped heavily with n-type impurity near the contact junction. So let's move towards the third problem. It says that we have some Schottky contact. Let's consider for the here it's given as an n-type semiconductor. Now we have Schottky contact, and phi m is much greater than phi s. So we have applied some negative bias with respect to the n-type semiconductor. Now this will distort our equilibrium. So it has been told that how does the magnitude of this electric field and the width of the depletion region change as compared to the equilibrium case. Now, if I say, as we have already seen this, we do not need to again derive it over here, that if we have some depletion width, this depletion width will correspond to some maximum electric field. Let me write down for Schottky contact, for Schottky contact, since we are just interested in the magnitude, the magnitude the magnitude of peak peak electric field is simply given by, if I write it simply as the magnitude, it will simply be given by q times the donor doping, that's Nd, into Xt, which is the depletion width, divided by epsilon s. So in here uh, we have Xt, that's depletion width, that is bias dependent, and rest of the quantities are independent of the bias. Let us concentrate on this Sd. This Sd is the depletion width with this depletion width is given by q epsilon s, phi bi minus Va, which is the applied potential, divided by Q and D, with this whole under the square root. Now, in here, this Va is applied bias. So this is the applied bias here. Now, if we consider the equilibrium case, then this Va will simply be equal to 0. And in case of reverse bias, reverse bias, this Va is negative. Simply, it will be negative. This Va is some reverse bias voltage Vr, where this Vr is greater than 0. So it will imply in this equation we will get xt equal to 2 times epsilon s, where phi bi is the built-in potential. Phi bi is the built-in potential. This subtracted by Va minus of Ea plus this will give me equal to plus Vr divided by, this will be divided by Q times Nd. Since this whole term is under now the square root, and clearly over here, if this Vr is increased now, so this Vr will simply increase the depletion width. This Vr increases the depletion width, and this in turn increase the magnitude of the peak electric field. So we can simply say that in this case, that the peak electric field and the depletion width both increase simply. Now let's move to the another problem. It says that we have been given some metal, and the metal is the chromium, and this metal is in contact with the n-type semiconductor, and it forms some metal semiconductor junction. And this semiconductor is doped with the doping concentration of 10 to the power 17 per centimeter cube. We have been asked to find the Schottky barrier height and the built-in potential. Here we have been given the electron affinity values. We have been given the band gap of the silicon. So the material is silicon. We have been given the effective density of states at the conduction band edge and the valence band edge, and also we have been given the dielectric constant for the silicon, which is 11.9. So let us begin by drawing the band diagram, how it would look like. For this case, if I draw the vacuum level, it will simply look like this. This will be the vacuum level. Since it will be a Schottky contact, it will look like this. This will be the vacuum level, and let me draw the Fermi level as dotted. So if this is the Fermi level and this is the conduction band, so we'll be having some, sorry, it will be simply like this, and it will simply be equal to Q phi B. And we will simply, one second, I think there is some issue with the internet. Oh, it's okay now. I think it's okay now. Yes, it has come up over here. So this phi b is the uh, barrier height, and this will be the valence band, which will be over here. This will be our valence band. Now in here we need to find the built-in potential as well, and the built-in potential will simply be, if I draw it like this will be the built-in potential, and this will be the phi f simply. And since this is the band gap Eg, this is the band gap Eg, this is the metal work function Q phi m. So if I now use the potential balance, let me insert some slides. So if I use the potential balance over here, I will simply see that this Q phi B should be equal to the built-in potential plus the Q phi F. So simply it will simply be equal to Q phi B will simply be equal to Q phi F, Q phi F plus Q phi Bi, which is the built-in potential. Now we have been also told to find the this thing. This is the what is the Schottky barrier height. The Schottky barrier height, this is from energy balance. Energy balance, can use energy balance or potential balance, however we like. This Schottky barrier height will be given by this Q phi B will simply be given by Q phi M minus chi S. Now let us check the values for these. Q phi M is 4.5 and this electron affinity is 4.05. So it will simply be 4.5 minus 4.05. So it simply will turn out to be equal to 0.45 electron volts. This is the Schottky barrier height. Now we have found the Schottky barrier height. Since we need to find the built-in potential, and from the equation number 1, that is the energy balance equation, we will get this built-in potential to be equal to simply equal to phi b minus phi f. Now let us find this phi f. This phi f will simply be equal to kT ln of Nc by Nd. This is what we have seen from the simply from the energy band diagram, that this phi f will simply be the ln of the Nc by Nd. Now let me put the values over here. This will become 0.026 into ln of Nc. It was 2 point something, 2.82 into 10 raised to power 19, 2.82 into 10 raised to power 19, and Nd I suppose was 10 raised to power 17. Yes, it was 10 raised to power 17. And simply let me solve this on my calculator. So it comes out to be equal to 0.15. 0.15. Now if I have to find the built-in potential, it will simply be the subtraction of the barrier height and this potential. This will simply be equal to 0.45, which came out to be the barrier height minus this 0.15, and this is 0.3 simply. So now let us check the options. The options in here is the option B, 0.45 and 0.3 volts. So the Option B is the correct option. Now this is having the unit of volts. Now let's move to another problem which says that we have the same metal junction as that in question number 4, but instead of n doping we have to consider the p-doped silicon with the dopant concentration of 10 to the power 17, and we have to find the similar quantities, that is the Schottky barrier height and the Puritin potential. So the difference in here will simply be, if I draw the energy band diagram beforehand, if this is the vacuum level E vacuum and this is the metal work function, this is 4.5 as we know, and this is the electron affinity. Electron affinity will simply be equal to 4.05 as it's given for silicon, and for silicon the band gap is 1.12, and if I add that over here, this will be the half of the band gap. This is the Fermi level, and this is the Fermi level which is intrinsic one, and this is actual Fermi level which is due to the p type of doping. So this means that this is equal to 0.56 electron volt, as this is a half of the band gap, e.g. this is the conduction band, this is the valence band. So that it means that uh, I wait a second, there is some issue with the connectivity. Let me again check it. One second. I think it's okay now. Yes. So it it now says that we have to find the barrier height for this case. This is the case which I have drawn. It is the p-type semiconductor. Now if I draw the Fermi level, now the electron transfer will occur from the metal side, and we will be having the abundance of electrons near the junction, so the bands will bend like this, that is the surface will have more n type, it will be having more electrons. So if I draw the energy band diagram, wait a second, there is some issue. One second, I'm really sorry for this. Sorry for the inconvenience. I have to share the screen again. Wait a second for this. So what I was showing you was that now I have to draw the energy band diagram for this. it will look like, if this is the vacuum level, if this is the vacuum level, E vacuum, and this is the Fermi level. Since the electron transfer has occurred from the metal side, now there will be abundance at the contact, the abundance of the electrons at the contact. Let me draw it like this so that it's clear. So this will be the conduction band. This will be having more concentration of electrons near the surface. This will be the valence band, and this will be the band gap. This will be the Q5F. This will simply be the built-in potential. This is simply the built-in potential. Now, this is what the barrier height will look like to this. This is Q5B, and this is the, as usual, our metal work function. So now this is the metal work function. So now if I use this energy balance again, I will be getting the if I go over the loop, I will be getting Q5B plus this metal work function Q5M. This will be equal to summation of this electron affinity plus the band gap. This will simply be equal to the summation of the uh, band gap plus the electron affinity. Now, if I simply write down this value, this will simply mean that I have to substitute these values over here. I will simply substitute these values to get the barrier height. This phi b is simply the electron affinity now plus the band gap minus the this metal work function. This will simply be equal to 4.05 plus the band gap for silicon, which is 1.12, minus the metal work function, which I told is 4.5. So it will simply mean this, if I add these things and write down the answer on the other slide, it will mean that this is equal to 0.67 electron volts. So this is the barrier height that we got. It is coming out to be equal to 0.67 electron volt. Now for the built-in potential, for this built-in potential, we will simply be having Q5bi will simply be equal to the phi b, which is the barrier height, minus the phi f. So if I now solve this for this phi f will be given by kT by q ln of nv by na. Now this is equal to 0.026. Simply nv was, I think, na is 10 to the power 17, na is 10 to the power 17, nv is 1.83 into 10 to the power 19. So nv is 1.83 into 10 to the power 19 divided by 10 to the power of 17. Let me put these values on my calculator and calculate the value that I will be getting. So it comes out to be equal to 0.14 volts. Now this is phi f.
we need to find the built-in potential, which is phi b minus phi f, and phi b came out to be equal to 0.67 minus 0.14, and it will give us 0.53 volts. Now let's check the options. This is 0.67 and 0.53, and only option C matches our choice. So we will go with option C. Now we have been given some question which is related to the previous question also, the fourth question. It says that we have some chromium metal, which is the same case as the previous one. This metal is in contact with the n-type semiconductor, and this semiconductor, we have, in this case we have been given some reverse bias. So in this reverse bias, we have to find the depletion width and the electric field that will be at the semiconductor interface. Now let us solve this problem by simply taking the help of the previous values that we got. That was the built-in potential. Built-in potential was, let me check, for this n-type was 0.3 volts. It is 0.3 volts, and the applied bias is 5 volts. Now let's solve this problem. This depletion width xt is simply given by 2 times epsilon s phi bi minus times Va divided by the Q times electronic charge times the doping concentration. So it will simply mean this will be equal to 2 into 11.9 is the dielectric constant, relative dielectric constant for the silicon. This is 11.9 into 8.85 into 10 raised power minus 14. Since we are dealing in centimeters, this will be 0.3 plus point, sorry, 0.3 plus 5 volts, not 5.5 volts, which is the applied bias, divided by Q is the electronic charge into 10 raised power minus 19. Doping is 10 to the power 17 as given in the previous problem. This whole term will be under the square root. Now let me solve this problem on my calculator. 2 into 11.9, 8.85 into 5.3 divided by 6. So it will come out to be equal to 0.26 into 10 raised power minus 6 meters, which is 0.26 micrometer, since the answer we require is in micrometer. So 0.26 is the depletion width that we are getting, this 0.26 micrometer. Now we need to find the electric field at this metal semiconductor interface. So the the electric field electric field is at this metal semiconductor junction is simply equal to the mm, the peak of this electric field at x equal to 0 will simply be given by Q times the doping into the depletion width divided by the epsilon s. So this is having the value of 1.6, the electronic charge, into 10 raised power minus 19 into 10 to the power 17 into 0.26 into 10 raised power minus 4 volt per meter centimeter. Since we are interested in volt per centimeter, that's why we have used the centimeter units. So this will be 11.9 into 8.85 into 10 raised power minus 14. So simply, if I solve this now on my calculator, Let's solve this. So it will come out to be equal to 3.95 into 10 raised power 5 volt per centimeter. Now let's check the options for this problem. So it is the option A, 0.26 micrometer and 3.95 volt per centimeter. Let's move to the another problem which says that we have been given the same metal semiconductor junction, and this junction now is also reverse biased with 5 volt of reverse bias, and the potential drop across the junction needs to be calculated, and also we need to find the junction capacitance per unit area. Now, if I solve this question at the thermal equilibrium, we will be having this built-in potential. So, at thermal equilibrium, the potential drop, the potential drop across the semiconductor is simply equal to the built-in potential. It is simply equal to the built-in potential, and that built-in potential in our case was 0.3 volts. Okay, it came out to be equal to 0.3 volts. Now at some reverse bias which is of 5 volts, this will appear across this semiconductor junction, and the metal across the metal there will be negligible drop. So let me write it down like this. If we have external bias VA is applied, this will appear, this external bias VA will appear across the this semiconductor, because the uh, metal the metal and the drop, and let me write it down like this, the drop across the metal will be will be negligible, so the drop drop across this semiconductor is simply equal to the phi bi minus VA, where this VA is the applied potential. Now this phi bi we know is 0.3, and this VA, since it's the reverse bias voltage, will be minus 5 volts. It will be plus 5 then, so it will become 5.3 volts. So this is the drop across the semiconductor. Now the second part of the problem says we need to find the junction capacitance per unit area in the units of nanofarad per centimeter square. So let's insert some slides and solve this. So this junction capacitance is the depletion capacitance. Simply it is the depletion capacitance per unit area in reverse bias. So this Cj will simply be given by epsilon s by the depletion width. This will simply be 11.9 into 8.85 into 10 raised power minus 14 divided by the depletion width. Let's see what it came out to be. In the previous problem we solved, it was 0.26 micrometer. So it will simply be equal to 0.26 into 10 raised power minus 4, and this will turn out to be, if I solve it on my calculator, so it comes out to be equal to 4.05 into 10 raised power minus 8 farad per centimeter square. But we had told to find it nanofarad centimeter square, so we will write it to be 40.5 into 10 raised power minus 9, that is nanofarad per centimeter square. So it will clearly go to the option C. So the option C is the correct option to select from. Now let's move to the another problem. It is the question number 8 of this assignment 5. It says that the capacitance C of a Schottky diode is given by some relation which is 1 by C square is equal to A minus B times V, where this V is the applied voltage and these A and B are some constant coefficients. Now we have been told to find the built-in potential and the donor concentration, and we have been told that the permittivity of the semiconductor is epsilon s and the junction area is given by A. So let's approach this problem by simply writing the depletion width expression. Let us use black pencil and insert some slides, one or two. So if I write down the depletion width expression, xt will simply be given by 2 times epsilon s phi bi minus the applied voltage V divided by the q times electronic charge times the doping. So this junction capacitance, if I see, is given by this junction capacitance is given by Cj is given by epsilon s A by xt. So it will simply mean epsilon s A by xt is the depletion width 2 times epsilon s phi bi minus V. This will be under square root, and the Q and D will now come in the numerator. So this expression will simply resolve to epsilon s uh, will be Q and D epsilon s. If I just write this Cj junction capacitance by C denoted by C and take the reciprocal directly, let us do that directly. It will become 1 by C will simply be equal to 2 times epsilon s phi bi minus V divided by epsilon s A by Q and D. Check the square root terms. So now let us square on both sides. So it will become 1 by C square is equal to 2 times epsilon s phi bi minus V divided by epsilon s square is a square by Q and D. This epsilon s and this will go, and we will simply be left with 1 by C square is equal to 2 times, this will be 2 times phi pi divided by epsilon s a square Q and D minus V by minus 2V by epsilon S A square Q N D. Now let me compare this expression. Let me denote it by 1 and compare it with the given expression, which is 1 by C square equal to A minus BV. That is 1 by C square is equal to A minus BV. So compare equation 1 and 2, we get A will simply be equal to 2 phi bi by epsilon s A square Q and D. So it will simply be equal to 2 phi bi by epsilon s A square by Q and D. Epsilon s A square Q and D. So we have got the value for A, or for the built-in potential. For the built-in potential, I can simply write it to be equal to, this will be epsilon s A square Q and D A, with this some constant, by 2. So this is the built-in potential that we were required to find. This phi bi or phi b, this is one and the same thing. Now b, if we compare b, b will simply be equal to, from this expression, 2 by epsilon s A square Q and D. It will simply be equal to 2 by epsilon s A square Q and D. Or simply for the ND doping, we will get it equal to 2 by epsilon s A square Q times B. So I have got the values for both the built-in potential and the doping. Now let us check epsilon s A square Q and dA. Epsilon s A square Q and dA. So option B seems one of the options, and for this it's 2 by epsilon s A square QB. 2 by epsilon s QB, 2 by epsilon s QB. So the option B is the correct option to go with. Now let's move to the another problem. It says that we have some metal. This is some different problem now. It says that we have some metal. uh, uh, this eighth and ninth problem is not related to the previous question. These are some new problems. So this metal semiconductor contact is with the AU. AU is gold, and this gold is having the work function of 5.1 electron volts, and the n-type n-type doped semiconductor is silicon in this case, with the doping of 10 to the power 15 per centimeter cube. Now this metal contact is kept 5 volts below the semiconductor. So we have been asked to find the electric field in the semiconductor, which is at a distance of 1 micrometer from the junction, and the temperature is given to be equal to 300 Kelvin, and the effective density of states at the conduction band edge is given to be equal to 2.82 into 10 raised power 19 per centimeter cube, and the electron affinity for this silicon, this semiconductor here is silicon, is given to be equal to 4.05, and the value for the relative permittivity in this case is given to be equal to 11.8. Now let us simply write down the expression for the electric field inside the semiconductor. So the electric field field inside the semiconductor will simply be some function of x will simply be Q times ND by epsilon S. X is some arbitrary distance from the junction, and this xt is the depletion width. Now we know the expression for the depletion width. It is simply Q and D by epsilon S. X minus this xd is given by 2 times epsilon S. Phi bi is the built-in potential minus Va by Q and D, with this whole under the square root. This means that we need to find the built-in potential first. Now, if I look into the expression for built-in potential, it is simply equal to phi bi is the built-in potential, and this is equal to phi b minus phi f, where this phi b is the Schottky barrier height. Now let's insert some slides. This phi b, we know this phi b is simply given by the difference of, since it's a Schottky barrier contact in case of n-type semiconductor, so this will be equal to simply the difference of the metal work function minus the semiconductor minus the what we have here, the minus the electron affinity, semiconductor electron affinity, which is chi s, and this metal work function is equal to 5.1 electron volts, and this chi s is equal to 4.05 electron volts. So it means we have simply 5.1 minus 4.05 electron volts. So it will simply be equal to 1.05. So we have got this barrier height to be equal to 1.05 in terms of volts. So this phi f will simply be given by phi d, that is kt by q, ln of nc by nd. Let me put it over here. The expression for phi bi will simply be equal to now 1.05 minus 0.026 ln of nc. This nc is having the value of 2.82 into 10 raised power 19. So it is having the value of 2.82 into 10 raised power 19. So it is 2.82 into 10 raised power 19 divided by the 10 raised power 15, which is the doping concentration for this 10 raised power 15. Oh, wait a minute, there is some issue with the internet. Now it's fine. So it is 10 to the power 15. Now if I solve this, let me solve this ln, it will come out to be equal to 821. It will simply be equal to 1.05 minus this quantity. It will simply be equal to 0.78 volts. This is the built-in potential that we got. Now from the expression, previous expression that we had got for the this electric field, let us substitute the values in this equation 1. This ND is having the value of 10 to the power 15, and phi BI, the built-in voltage we got, it came out to be equal to 0.78, and VA is the applied bias, and it is the reverse bias, that is, it will be minus 5 volts. So let us substitute these values in that expression, and we will be getting this electric field at some distance, that is 1 micrometer from the uh, junction. I will be getting Q in Q and D by epsilon S. This will simply be 1.6 into 10 raised power minus 19, and D is 10 to the power 15, divided by epsilon S is 11.8 into 8.85 into 10 raised power minus 14, simply. And this X is 1 micrometer. In centimeter, it will be 10 to the power minus 4. Minus times this xt is simply 2 times epsilon s. It is 2, let me put it in the square root, 2 into epsilon s, 9.8 into 8.85 into 10 raised power minus 19 into the phi bi minus va, which is 0.78, plus 5 divided by, this is 10 raised power minus 14 over here, 1.6 into 10 raised power minus 19 over here, into 10 raised power 15. Let me solve this expression on my calculator and write down the answer for this. This E at x equal to 1 micrometer, it will simply come out, if I solve this expression, 2 into this thing, so square root, so it will come out to be equal to, after subtraction, it is minus 26.76 into 10 raised power 3 volt per centimeter, that is kilovolt per centimeter. Now let's check the options. It is the option C which is matching our options. So we will take the option C over here. Now let's move towards another problem, which is the last problem of this assignment 10. It says that we have been given the statements regarding the metal semiconductor junction. It states that we have 4 statements and we have to find which of the following is incorrect. So first statement says that thermionic emission depends on the shape of the band bending inside the semiconductor near the junction. So this statement is clearly wrong, because this thermionic emission, it depends on the barrier height, which is the main factor, and the temperature as well. So it thermionic emission does not depend on the band bending inside the semiconductor, this junction. So we can clearly say that this option A is the correct option for us, since it is the wrong statement. But let us go through the other problems as well. It states that tunneling current through a triangular barrier increases at the junction with the doping concentration in the semiconductor. This is clearly true, because if we increase the doping, this barrier will get thinner and thinner, and we will be having steeper thing, so the electrons will tunnel through more easily. And diffusion transport through a junction is negligible in case of reverse bias. This is also correct. So the thermionic, the last option is the thermionic emission
transport increases with the enhances with increase in temperature, which is the correct statement because this is true. So in here, the option A is the option that we should go with. So in this live session, we have solved the assignment 5, and in the next session, we will be solving the assignment 6. So I will be concluding this live session for today as it's already 6. So let me end this session. See you in next session. Thank you very much.